Hi folks, now we're going to go to the next section, which is to talk about science in a general way. And I'm going to start off with, first of all, a couple comments. One is that astronomy is a science. We're not doing astrology here, although we may talk about the connections between astronomy and astrology later. But astronomy is a science. And one of the key things about science is this quote from Richard Feynman. There are lots of people that have come up with quotes, and I'll be expressing these quotes to you, but this one is a good one to start this particular section off. And, you know, the basic idea is that we don't want to be fooled. Okay, so science is a way of trying to not fool ourselves. But there are a number of other ways of viewing science. You can view it as a process. It isn't just a bunch of facts and data, although facts and data are a part of it. And Richard Pogge has this nice idea of science as a way of dealing with what we don't know. The connection between facts and data and the fact that we don't understand everything. That we don't understand everything is not to be feared, but in fact, it is something to be celebrated because it allows us to explore. And exploring is one of the fun things in life. Science is empirical. It's not wholly dependent upon reason or revelation, but it is something that we share. Okay, revelation is something that is entirely personal. Some people say that that's a brand of knowledge, but it is not something that we can share between individuals. You can have a revelation that could be similar to somebody else's, but it's going to be entirely unique to yourself. Couple other comments one can make about science is that you can turn it into a religion, and that's called metaphysical naturalism or scientism, and it's not to be confused with the philosophical basis of science and basically the assumption that science works, and that's called methodological naturalism. Logic can take us quite a distance, but the nature of logic is inductive or deductive arguments. And so the simple idea of trying to prove that the sun will rise tomorrow is something that is outside of these two, which can't be logically proved. Logic is based upon things that you already know and things based upon the past, so you can't move them into the future. Science can. One of the key notes of science, or the key premises of science, is it allows us to make predictions. And from those predictions, we can validate whether or not a theory has any relevance at all. So, anyway, another way of, a final way of viewing it is science assumes that nature plays by rules, and ultimately we can figure out what those rules are. Here are some examples. Things that burn, water combining into carbon dioxide plus solar energy gives a green plant and oxygen, and we can go the other way around to plant materials plus oxygen give off water, energy, and carbon dioxide. But one needs to be careful, though, in the sense from Arthur C. Clarke's third law, that any sufficiently advanced technology is indistinguishable from magic. A very interesting idea. So, for example, if you bring a laser back 100 years in time and shot at Abraham Lincoln's eyes at the Ford Theater, you could have probably killed him, which would have gotten Mr. Booth off the hook, and you would have been undetected. And that whole idea of setting somebody's hair on fire would have gotten you in a big amount of trouble still, but you would have been burned at the stake as a witch. One of the things about science is we have to be very clear about our vocabulary. I talked about that before in our introduction, and here's where we're going to start to see the reason why. The later reasons why are going to be entirely contextual and will allow us to speak about certain topics. But I talked a little bit about velocity, acceleration, things like that. But it isn't the accuracy so much as the clarity of meaning. And with science, you have to communicate to other people. Science is a body of knowledge and ideas that we share. In order to share these ideas, we have to be clear about what we mean. So terms like I show here are quite specific. They mean certain things, and they allow us to describe relationships. Here's a few ideas I want to get across to you now that may be a little confusing in their totality, but they have specific meanings. A fact, a hypothesis, a law, and a theory. You sometimes have heard that evolution is just a theory. Well, it's just a theory in the same fashion that the law of gravity is just a theory as well. Both theories are predictive in nature. We can alter the situation for whether or not a critter will survive or not. And for example, hundreds of examples associated with evolution. Certain bacterium are becoming more and more resistant to chemicals that we use to kill them off, and that is just the nature of genetics. The bacterium is evolving to become more resilient to a bath of chemistry. A hypothesis is basically a tentative statement about the world, which we utilize to see if we can create a theory from it. And a fact is entirely different. A fact is something that we observe, and it can be repeated, and anybody can observe it. Anybody can repeat the experiment and get the same sort of data. Now, there is a caveat, of course, and that has to do with you have to have the right instrumentation. But in science, we basically are not hiding the evidence or how we do things, and therefore the facts are readily available to everybody. If you can't make predictions, then you can't test a hypothesis. You need higher level thinking in order to do this science. And Poincaré had this idea about science. It's built up of facts. It's like a house with stones. But a collection of facts is no more science than a heap of stones is a house. So basically, the theory allows us to describe these facts in a cogent, coherent fashion. And we don't need to then carry around all the stones in order to understand the world around us. All we have to do is go in the house and sit on the couch with a nice drink with an umbrella in the glass, and with a sleeping dog on the rug. Now, science, especially when we take data, is really an approximation of the truth. The primary example I'm going to utilize is flat Earth versus a round Earth, and I'll be using this throughout the semester. The idea of a flat Earth is painfully obvious. We build houses, bridges, buildings, roads, as if the Earth was flat. You put a ball on the outside, and the ball will run down the gutter or so, but at some point it will stop. Now, you know for a fact if you put a ball on top of another ball, the ball will roll off and go out into space someplace. And that is not what we see happening around us. When we walk distances, we presume that the Earth is flat. I mean, you look outside, it's obvious it's flat. But at some point, the curvature of the Earth arises and causes us to make mistakes. Make mistakes about where we ought to be given the direction of travel. Make mistakes of what we should see if the Earth was flat versus if the Earth was round. And an example that's close by to us is if you go over to Palos Verdes and you look over at Catalina Island on a clear day. And if you are at the top of the hill, say at Del Cerro Park, you look across and you'll see one island. If you travel down to the beach, say at Abalone Cove, then if you look across in the same direction, you will see two islands. You'll see two islands separated by the water. A flat Earth would not predict such a situation. A round Earth would. Now, it doesn't mean to say that the two theories are that the flat Earth is wrong. In a sense, it does, but the sense is that at a higher level, we have a better theory that describes stuff. But let me remind you, when we build houses, you don't have to account for the curvature of the Earth. We still utilize the fact that the Earth is flat to build a house. Now, an analogy like this can be employed to gravity. Newton's laws work really well, and we utilize them all around in the solar system. But at some point, the theory fails, and we have to use Einstein's theory of relativity to talk about gravity. And that's what Guy Cosamago is talking about here. Science is an approximation of the truth, and as we learn more things with higher precision, then we naturally learn more, and we find more things that are wrong with our basic understanding. Some people would lead you to believe that that is it's evidence of a God, if you will, because we can know, we can never know everything. There are a couple of ways of viewing science. A theory is constructed as indicated in the chart on the left. You make observations, you ask a question, you make a guess, a hypothesis. That allows you to make a prediction, and then you test again. If the test supports, or rather, if the test creates data that supports your theory, your prediction was true, then you got a theory. If it doesn't, then you got to go back to the drawing board and create a new hypothesis. There is a game out there called the hypothesis guard game, which is something we play in the face-to-face class, which if you run around on the internet, you might find it, and that would be something fun to play with. The ideas on the right-hand side, the hallmarks of science, really show you the process involved in the totality. The way that we construct a theory is what has going on the left-hand side. But science has the, is basically connected with, we make testable predictions, and if the model doesn't work, we got to throw it away. We try to utilize, make theories that are the simplest thing rather than, it's called Occam's razor. The theory that is the most sensible, requires the least amount of explanation, is probably the one that is correct. How do you do science? Well, it starts with curiosity. As we saw before, you make a guess, you test, you allow for uncertainty, you test and test and test, and sometimes you find things that work and sometimes things that don't work. This was the original model associated with the atom. It's called the Thomson atom, plum pudding model, if you will. And this was the Rutherford atom, which is one that's closer to our current understanding of atoms. Big theories: Newton's laws of motion, the atomic theories, plate tectonics, stellar evolution, biological evolution. These are really, really on firm ground. In practice, somehow people have to be given enough support so they can earn a living, support their families, eat. You need the equipment. You do the observations or the theory, experiment. You publish. And typically the publications are refereed, meaning somebody is looking over your shoulder. And if you come up with something that doesn't quite work, then other people certainly become interested. And that being the case, then other people will try to prove that you're wrong or verify that you're correct. Scientific inquiry is not perfect, but it is rather self-correcting. It's, we're human and we do make mistakes. Sakai created, and Sakai wrote a paper associated with psychology and its overlap with physics, and basically got it published even though it didn't mean anything. And then if you look up this one, Bogdanov affair, he wrote stuff up that didn't make any sense either and somehow got it past the referee. So things can, it's hopefully but tricky is a good idea. But the key thing, one of the key things about science is you got to be a keen observer. You have to look at the world around you. And that's one of the things that's been really joyful for me. Because I still consider myself a scientist. And when I go out to the mountains, I'm probably the quickest person on the draw as far as seeing the deer that's far away, or the snake, or the coyote, or this or that other creature. Looking at the differences between in the world in front of me, and I can see what's going on. So it makes it more engaging. Now, if it can't be disproved, it isn't science. And I want to show you this YouTube video from Feynman, and we'll see if it plays up.
Now I'm going to discuss how we would look for a new law. In general, we look for a new law by the following process. First, we guess it. Then we so don't laugh, that's really true. Then we compute the consequences of the guess to see what, if this is right, if this law that we guessed is right, we see what it would imply, and then we compare those computation results to nature, or we say compare to experiment or experience, compare it directly with observation to see if it works. If it disagrees with experiment, it's wrong.
Here comes the hand waving. I love
And
it.
that simple statement is the key to science. It doesn't make a difference how beautiful your guess is. It doesn't make a difference how smart you are who made the guess or what his name is. If it disagrees with experiment, it's wrong. That's all there is to it.
Yeah, here he talks
It's
about flying
therefore not
saucers.
unscientific to take a guess, although many people who are not in science think it is. For instance, I had a conversation about flying saucers some years ago with laymen. Because I'm scientific, I know all about flying saucers. So I said, I don't think there are flying saucers. So my antagonist said, is it impossible that there are flying saucers? Can you prove that it's impossible? I said, no, I can't prove it's impossible. It's just very unlikely. That, they say, you are very unscientific. If you can't prove it impossible, then how can you say it's likely, that it's unlikely? Well, that's the way, that is scientific. It is scientific only to say what's more likely and less likely, and not to be proving all the time possible and impossible. To define what I mean, I finally said to him, listen, I mean that from my knowledge of the world that I see around me, I think that it is much more likely that the reports of flying saucers are the result of the known irrational characteristics of terrestrial intelligence rather than the unknown rational efforts of extraterrestrial intelligence. It's just more likely, that's all. And it's a good guess. And we always try to guess the most likely.
Okay, so that being said, it probably I'll leave you on this picture here for lights in the sky, and how to identify that light in the sky. Right now, currently, it's overcast and things like that, but on a clear night lately, Venus is really showing up really brightly. And Venus showing up brightly would be over here. But is it really big? Well, no, it isn't really big. Was it moving? Well, not really. So I come over this way. Was it twinkling? No, it wasn't twinkling. It was kind of fuzzy. Although I have seen planets that do twinkle, especially when they're low in the horizon, and they do move when it's very windy out. But we'll talk about that when we talk about twinkling of stars. So basically, this gives you a whole list of things it could be. And a couple little charts about little green men. We've been fooled, scientists have been fooled in a couple ways by little green men. One is from quasars, quasi-stellar objects with lots of radio waves, and the other one being neutron stars. So, you've seen these pictures of the face on Mars. Later on with more data, you see that it was just a hill. Pseudoscience uses the language of science without the process. What to look for is, as Deep Throat said to the Washington Post guys, find where the money is going. And that will lead you to the right location. So, intelligent design, look at the NOVA program, Intelligent Design on Trial. Intelligent design does not provide any predictions, just talks about what possibly could happen in the past, but it's based upon a Godhead normally. Astrology, does it work? Well, I have a set of twins. According to astrology, they should behave exactly alike, and they don't. We could also take a look at, historically, in terms of planets. For a while, Ceres was used as a planet in astrological charts. Pluto has been. It's been demoted. Why is it still there? What about Eris? It's 20% more massive than Pluto. Why isn't it in the charts? Why weren't these charts, having planets that were discovered later on, like Uranus and Neptune, in charts before they were discovered? Shouldn't astrological people notice that? And then, this is an in-class example we do in the face-to-face class. And another one is this. One can test the president's birthdays as a means to understand astrology. Astrology is supposed to talk about the personality traits of an individual. I would say that you can also describe the personality traits of an individual from the choice of their employment. A fireman or a president of the United States. And given that, they should have similar characteristics. They should show up in their personalities, and therefore in their sun signs. That is, if this description of astrology and sun signs work. And if you do it on the presidents, you should have a clustering of presidential birthdays around a particular sun sign. And when you look at it, you don't. It's all over a distribution that is flat across the sun signs. All right, that being said, there's other data that you can look at associated with astrology that doesn't work. But basically we're talking about theories, predictions, and in that regard it is not a theory that would work. So you need to throw it away. Why do people still believe? And this also applies to critical thinking. You could say that, at least for astrologers, they're doing a cold reading on you. People are very similar. So you do the effect on one person, or you read one person and you can apply it to somebody else. And the last one is you want to get your money's worth. So you spend money, you give an astrologer some money. You want to make sure that it's believable, and that you want to get your money's worth out of it. So yeah, you remember the successes that they had, forget the failures, and convince yourself that they were right. All right, so that being said, we'll continue on with